Hello, my name is Zhenjian Lu. I'm going to talk about the complexity of avoiding heavy elements. And this is a joint work with Igor Oliveira, Hanlin Ren, and Rahul Santhanam. And let me begin with a summary. And in this paper, we introduce a lecture computational task called the heavy avoid problem. And we then show that the complexity of this problem is tightly connected to frontier open questions in complexity theory. And more specifically, we show that efficient algorithms for solving the heavy avoid problem have significant implications for long-standing open problems, such as proving lower bounds against uniform probabilistic circuits and de-randomization. And some of these implications are even if and only if. And additionally, we obtain unconditional pseudo-deterministic algorithms for solving the heavy avoid problem. And let me first give an informal definition of the heavy avoid problem. And let D be a distribution over n bits. Here we use capital N. And let delta be a number between 0 and 1. And we say that an n-bit string X is delta heavy with respect to D if the probability that X is sampled from D is at least delta. And our task is to deterministically find an n-bit string that is not delta heavy. And in other words, we want to avoid a heavy element. And first, note that as long as delta is greater than 1 over 2 to the n, and there's always a solution to this problem because the number of delta heavy strings is at most 1 over delta, which is less than 2 to the n. And also, if delta is somewhat large, then a random n-bit string is a solution with high probability. And therefore, heavy avoid can be easily solved using randomness. And here, we are interested in solving this problem deterministically. And as mentioned earlier, we explore the connections between heavy avoid, lower bounds, and de-randomization. And we also consider unconditional algorithms for solving heavy avoid. So let me first talk about proving lower bounds against uniform probabilistic circuits. And let A be the circuit, be the complexity class that is one of NP, P space, exp or exp with NP oracle. And the major open problem in complexity theory is to show that the class A is not contained in BPP. And in particular, we don't even know how to separate exp with NP oracle from BPP. And in fact, many of these questions remain open, even if we just want to show that these classes cannot be computed by some uniform probabilistic weak circuits. And to describe this more formally, let me define uniform probabilistic circuits. And let C be a circuit class such as ACC0, TC0, or NC1. And we say that a language L is computable by D-log-time uniform probabilistic C circuits of polynomial size if there's a sequence of C circuits E, each indexed by a number n, such that E is D-log-time uniform. And this means there's a deterministic algorithm that, given a number n and a pair of gates U and V, determines in O of log n times the gate types of U and V, and whether U is V's parent in the circuit E sub n. And for this talk, we can just think of it as that the sequence of circuits can be determined in a uniform and certain efficient manner. And also for the rest of this talk, we will use uniform to mean D-log-time uniform, unless stated otherwise. And additionally, each E sub n is a poly n-size probabilistic circuit that computes L on inputs of length n. And in other words, the circuit takes an instant X and the randomness R, and with probability at least 2/3 over the choice of R, it outputs whether X is in the language L. And now again, let A be the complexity class that is one of NP, P space, exp or exp with NP oracle. And let C be a circuit class such as ACC0, TC0, or NC1. And the problem is to show that A does not have uniform probabilistic C circuits of polynomial size. And as mentioned earlier, for almost all choices of the complexity class A and the circuit class C listed here, the corresponding question remains open. And one exception is for exp with NP oracle and ACC0. And it follows from the non-uniform ACC0 lower bounds by Williams that exp with NP oracle does not have uniform probabilistic ACC0 circuits. And now let's return to the heavier wire problem and see how it is related to the lower bound problems that we just described. And recall that in the heavier wire problem, we are given a distribution D and a number delta, and we need to find a string that is log delta heavy. And the first question that we need to address is how the distribution D is given. And we will be given a circuit that samples the distribution D, or something called a sampler. And more specifically, let D be a distribution over n bits. An explicit sampler for D is a circuit G that maps some R bits to n bits, such that the output of G is distributed according to D for uniformly random R bit inputs. And therefore, G can be used to sample the distribution D using a random string. And note that since G outputs the entire n-bit string in this case, it must have size at least n. And sometimes it is possible to specify a distribution in a more compact way. And more specifically, an implicit sampler for D is a circuit G that takes as input a random string and an index between 1 and n, and it outputs 1 bit, such that the n-bit strings obtained from running G on all the indices from 1 to n is distributed according to D. And in this case, the circuit G outputs only a single bit of the n-bit string sampled from the underlying distribution. And therefore, G may have size much smaller than n, and for example, polylog n. And now we have that the distribution in the heavier wire problem will be specified by a sampler. And one option is to let the sampler be part of the input when solving the heavier wire problem. And however, we will also consider the setting where the samplers can be determined uniformly. And more specifically, let D be a family of distributions indexed by n, where each D sub n is over n bits. And let's say be a class of circuits. We say that D emits uniform implicit C samplers if there is a sequence of C circuits G such that G is uniform and each G sub n is an implicit sampler for D sub n. Similarly, we can define uniform explicit samplers for a family of distributions. Now let me state our first result. And let's see be any nice circuit class that satisfies some mild conditions. And we show that X does not have uniform probabilistic C circuits of polynomial size if and only if heavier wire for uniform implicit C samplers can be solved infinitely often in deterministic polynomial time. And the latter means that for any distribution family D over n bits that emits uniform implicit C samplers of size polylog n, and delta that is 1 over polylog n, there exists a deterministic algorithm A that, given the number n, runs in poly n time and outputs an n-bit string that is log delta heavy with respect to D sub n for infinitely many n. So here we characterize the question of separating exp from uniform probabilistic circuits by the feasibility of solving the heavier wire problem. And note that the type of uniform probabilistic circuits that we aim to show lower bounds against corresponds to the type of implicit samplers for which we need to solve the heavier wire problem. And on the other hand, the efficiency of the heavier wire algorithms corresponds to the hard complexity class in the lower bound statement. And in this specific case, the algorithm runs in deterministic polynomial time, and the hard complexity class is exp. And in fact, by considering different notions of efficiency, we can also characterize the question of separating other complexity classes from uniform probabilistic classes, from uniform probabilistic circuits. And for example, if the sand heavy avoid problem can be solved in deterministic poly n time with an NP oracle, then the hard complexity class in the lower bound statement becomes exp with NP oracle. And if it can be solved in deterministic O of log n space, then we get P space. And finally, if the heavy avoid problem can be solved by uniform circuits of consonant depth and quasi-polynomial size, then the hard complexity class will be NP. Now let's move on to our second set of results, which explores the connection between solving heavy avoid and de-randomization. And a famous conjecture in complexity theory states that every randomized algorithm can be efficiently simulated by a deterministic algorithm. And in other words, BPP equals to P. And however, it seems that we are still very far from proving this conjecture. And in this work, we show that if one can get an efficient low-depth algorithms to solve the heavy avoid problem for non-uniform implicit samplers, then BPP equals to P. And more precisely, there exists a constant epsilon and an algorithm A such that given as input an implicit sampler of size n to the epsilon for some distribution over n bits, A outputs an n bit string that is log little o of 1 heavy. And additionally, A can be implemented as a log space uniform circuits of size poly n and depth n to the little o of 1. And note that we are considering the setting of solving heavy avoid for non-uniform samplers, where the samplers are given as input to the algorithm, instead of a sequence of predetermined uniform samplers in previous cases. And also, we need to solve heavy avoid in a very efficient manner using a uniform circuit that has subpolynomial depth. And we obtained this connection through a recent hardness versus randomness trade-off result by Chen and Tao, which employs a notion called almost all inputs hardness. And we will consider this notion in a slightly different form than that presented in the original work. And the assumption of almost all inputs hardness states that for every polynomial P, there exists a polynomial Q and a function mapping n bits to Q of n bits, such that F is computable in deterministic polynomial time. And however, every algorithm running in randomized P time only locally computes f of x on finitely many inputs x. And here, locally computes of f of x means that for an input x and an index I, it outputs the ith bit of f of x with high probability. And basically, this assumption states that there exists some multi-output function that is computable deterministically in polynomial time. But any randomized algorithm that runs in some smaller polynomial time fails to compute it on all but finitely many inputs. And it is conjectured by Chen and Tao that almost all inputs hardness implies de-randomization. However, it is not yet known how this can be proved. And then they consider a stronger assumption about the existence of almost all inputs hard functions that can be computed efficiently with low depth. And let me call it almost all inputs hardness with low depth. And it is similar to the previous assumption, with the only difference being that instead of saying that the hard function can be computed in polynomial time, it can now be computed by a log space uniform circuits of polynomial size and subpolynomial depth. And with this extra low depth efficiency condition, it was shown that almost all inputs hardness with low depth can imply that BPP equals to P. And in this work, we show that the feasibility of solving heavy avoid for non-uniform implicit samplers is in fact equivalent to almost all input hardness. And moreover, for one of the directions, it is possible to show that if we have an efficient low-depth algorithm solving heavier void for long uniform implicit samplers, then we get almost all inputs hardness with low depth. And since the latter implies BPP equals to P, this is how we can show that a low-depth algorithm solving the heavier void problem leads to de-randomization. And the final part of this talk is about obtaining unconditional algorithms for heavier void. And as we have seen, solving heavier void can have significant implications for lower bounds and de-randomization. Then the natural question is, can we get unconditional fast algorithms for solving this problem? And note that heavier void can be easily solved by randomized algorithms. And on the other hand, fast deterministic algorithms implies breakthrough results, which seem to be challenging. So interesting question then is, can we get fast pseudo-deterministic algorithms for solving heavier void? And it turns out that we can obtain these algorithms unconditionally for both settings of uniform, implicit, and explicit samplers. And before discussing this result, let's record the notion of pseudo-deterministic algorithms. And when we have a randomized algorithm for a search problem, it produces a solution on most of its computational paths. And however, different computational paths may give different solutions. And on the other hand, a deterministic algorithm has only one computational path, and it always produces the same solution. And we say that a randomized algorithm is pseudo-deterministic if on most of its computational paths, it outputs the same answer. And in other words, it produces a canonical answer with high probability. And we showed that there are pseudo-deterministic polynomial time algorithms that solve heavier void for uniform implicit samplers infinitely often. And the proof of this result is actually pretty simple. So let me sketch it here. And we use a win-win argument. In the first case, we assume that X is locked in BPP. And by our characterization result, heavier void in this case can be solved infinitely often in deterministic polynomial time. And now consider the case where X is in BPP. And it is easy to see that heavier void can be solved in deterministic 2 to the power n time trivially. And this allows us to define a language in Exp that determines the ith bit of a fixed solution string. And by the assumption that Exp is in BPP, we can compute each bit of this string in randomized polynomial time. And this will give a pseudo-deterministic algorithm for outputting a fixed solution string with high probability. And we also obtain pseudo-deterministic algorithms for solving heavier void for uniform explicit samplers infinitely often. And in this case, we only achieve sub-exponential running time. And let me give some intuition behind this algorithm. And again, note that heavier void can be solved efficiently using randomized algorithms. And then by using a lone pseudo-deterministic PRG from the work of Oliveira and Santhanam, one can pseudo-randomize these algorithms. And this is basically the main idea behind this algorithm. And this concludes the talk. Thank you very much for listening.